Preset get moved? Huh. Preset got moved. Huh. Maybe I'm just a little bit. I just wasn't paying attention. There we go. So I want to talk about energy methods with universal gravitation. Before we do that, I want to kind of do a big picture review of some things that maybe you know from class, right? So earlier in the semester and a couple of times in a problem, let's say we want force or acceleration, we would often do an FBD and force equations. Now, sometimes we'd have to do torque, you know, but this was one of the things we did. If we wanted to determine for our given speed, we would often do an energy problem, right? There's some exceptions. In particular, one that jumps out at me might be constant speed in circular motion. While it's not always true, we typically do an FBD on that one, right? And force equations. So I'm trying to set you up for which physics tool do we grab to get the job done. Last time when we were doing universal gravitation, we did force problems, so we wanted to puke. A few times we wrote down the energy. What I want to try and focus on now is when you read a problem, I want you to think about, okay, if we're looking for force or acceleration, I should probably do an FBD. If I'm looking for a speed, I should probably do energy. That's not always true. In particular, circuit of motions, oftentimes, in particular, last class, we found the speed using an FBD because AC has the speed in it. So far, so good? And then we have another technique. We had constant acceleration kinematics, right? It doesn't always apply. Okay. For example, what if you had a swinging pendulum? As this pendulum swings, do you agree that the torque changes because the angle changes as a pendulum swings? So in this problem, the torque is not a constant, which tells us that alpha is not a constant, which says don't use constant alpha kinematics. So that's a review example. You remember that one? We want to avoid using kinematics on the pendulum because constant acceleration kinematics isn't valid. I have another example for you now, a new example. Let's say we have object 1 and object 2, and these are in outer space. There's a force of 2 on 1. By Newton's third law, there's a force of 1 on 2. In this case, the magnitude is g m1 m2 over radius 1, 2 squared. The magnitude is, right? Everybody okay with that? And by the way, right, you got the video. You don't need to write any of this down. I'm just trying to give you a feeling for this. You don't want to write this down. That's cool. We're trying to understand something, not write it down if you don't want to write it. Now look, if I release these two objects from rest and there's gravity, what's going to happen to them? They're going to come together, right? Is the radius going to change? Yeah. So R12 changes. What about force 1,2? Is that going to change? Yes. So is the acceleration going to change, or is it a constant? Is the acceleration equal to or not equal to a constant, in your opinion? What's that? Constant. It's not constant because it's force over mass. If force changes, A changes. Agreed? And maybe that's what you said and I didn't hear you, so I'm sorry. Okay. So why am I bringing all this up? For this reason. If we want to figure out the speeds of two objects as they're moving around, we do not want to do forces in kinematics anymore. Just like the swinging pendulum, we used energy. So if you're wondering why I'm bringing this crap up, it's that some problems are easier solved with energy methods than forces. So far, so good? Let's talk about the strategy involved. Okay. Usually, we would draw an initial and a final picture, right? So maybe we have mass 1 here and mass 2 here. And in the final picture, maybe it's just before impact. Okay. Then maybe in the final state, they're going hella fast. Right? So we have a before and an after picture. From experience, you know that the center to center distance matters. But it's not the same. So maybe we should say R1 to 2 initial and R1 to 2 final. You know what I'm saying? The center to center distance, initial and final, matter. And if, again, we're trying to do energy methods, what's the general energy equation that we have from chapter 8 or whatever it was? Does anybody remember that? Oh, you're doing, yeah, okay, you're going farther. I was going to say K initial plus U initial, and you were already plugging in. Yeah, got you. Nicole was saying, what do you plug in for the kinetic energy here in the initial state? And then because there's two of them, You know what I'm saying? You know this part. What do I plug in for U? No, that's only near Earth's surface. What's our new gravitational? You're thinking of MGH for a height above the Earth. Now we have 2 asteroids in space or something. What's the equation? Do you remember that from last time? What's that? Close. Negative G. You agree it was negative? Remember I kept emphasizing that? Now, while this isn't always true, we're going to restrict ourselves to things that are in outer space. How much air resistance do we got in outer space? Negligible. So we're going to drop out this work term. Wait a minute. Doesn't gravity do work? We have already accounted for the work done by gravity in the potential energy because it's conservative. Right? This is work done non-conservative. Since gravity is a conservative force, we already accounted for it. Okay, so we're going to drop this out. Now, to be clear, you can have drag if you're near a planet, right? Like the space station that collapsed and fell to Earth. Right? It was in the upper atmosphere, so there wasn't a lot of drag, but over several years, that drag could be just enough to cause the orbit to decay and crash into the planet. But we're going to ignore any drag terms for this class for outer space stuff. Cool? All right. And then over here, oh, I should be careful here. This looks kind of crappy. I want to put the minus sign here, right? Plus U initial has a negative sign in it. Then I better put the initial here. And you agree it would look very similar over there, except there'd be finals. Well, I'm just going to write it in here. Well, I think I did that in purple. Get out of the way just a second. There's the kinetics final, and then there's another minus term for the gravitational because it's a minus GM. Piece of cake, right? Feeling okay on that? All right. And then at this point, we can just apply this to different scenarios. So if you wanted, you could use these results to check your code. You could take 2 masses, release them from rest, have the code stop when they hit each other, and then say print out the final velocity and see if it matches what you expect. So it's a way to check the reliability of your codes. That's kind of cool. Interestingly enough, I don't know. Are you feeling good on that? Thumbs up, thumbs down. Where are we at? Or question, Peter? Or no? Thinking? Good. Everybody okay on that? Well, I got a question for you then. We go back to this other whiteboard and ask you one quick thing. In this problem, we just said that constant acceleration kinematics doesn't apply. And yet, when we were coding this, we used constant acceleration kinematics in the codes. Does anybody know why that's legal? The trick is this. In your code, we split the problem up into tiny time steps. And during one time step, the force is approximately constant, which means, right, so if you split this thing up into small enough chunks, the distance doesn't change that much. So the force doesn't change that much, which means the acceleration is approximately constant. So that's the trick with a code, is you can take a problem that on pencil and paper requires energy methods, and you make the computer split it up into such tiny chunks that we can use constant acceleration kinematics. That's kind of cool. Did that make any sense whatsoever? That's the advantage of coding, is you can use kinematics, whereas on paper and pencil, you just can't. And that's a big deal. All right, enough said. Should we try a problem? Let's try page 120, problem 13.9. It's going to take me a minute to erase. I'll be right there with you. Okay. Peter, you got all this side? Can I erase or no? Not yet. Start on this side?
Go ahead.
I'll start over here. Is that good?
Yep.
Okay. At least I caught myself this time, right? I go for it now. Okay, thanks. All right. Okay, I'm going to look at this 13.9. In our initial state, there's going to be this planet that has some mass, capital M. I think it's going to have exactly the same mass as the Earth, so I'm going to use capital ME. And the radius of this planet is the same as the Earth. I'll put some shading on here just to make it look a little pretty. Okay. And we've got a point mass here. For now, I'm going to assume it has mass little m. And this thing is going to be moving with speed v in the initial state. So it's at the surface, it has negligible size, mass m, and speed v, and it's going radially out from the planet. All right. In the final state, let's assume the planet is so huge it doesn't move at all. The planet's still there, but I want this little mass to get really far away. Okay. Now, it's an important problem. You should definitely put a star by it and redo it later. And you should probably pay attention to what I'm about to say right now, because these assumptions are things that physicists assume you know. And this same problem is going to show up again in Physics 163. This entire chapter we do again in Physics 163. It's almost identical, right, Alan? Remember, like all the problems that we do in this section, aren't they very similar to the point charge problems we do in physics?
Yeah, it's gonna be. It's exactly the same thing. That's gonna be the first chapter for 163.
So, yep. So it doesn't hurt to learn this well. Okay, and it's on your final. Okay. And we could discuss more about the types of questions at the end of the class today. Here's one of the things. there's some final distance. Okay, and that's going to be center to center. And then there's some final speed. In physics, we say if the object just barely escapes, we say it gets to an infinite radius with zero speed, which sounds pretty silly, right? Here's the idea. If you say it escapes, it should be able to get 10 billion meters away, or 100 billion meters away, or 1 to the 2 billion meters away, right? So that's, you could arbitrarily choose some distance as being really big in a code, like 1E97, or you could just call it infinity. Now, what does it mean to escape? It's got to get away from the planet and not fall back down. As long as the speed is bigger than zero, it's still slowly drifting away. So if it was 1 meter per second, it would still escape. If it's 0.1 meters per second, it would still escape. As long as the speed is any number above zero, it escapes. Good? So then the trick is, we set the final radius to infinity, we set the final speed to zero, and that's the limiting case. If it gets infinitely far away and then stops moving. Does that kind of make sense why I chose those parameters? All right, let's do an energy equation. K initial plus U initial equals K final plus U final. Why did I ignore the work? We're in space. We're ignoring air resistance. Is that realistic? Probably not. There's usually some atmosphere on this planet. Otherwise, this planet of the physicists, they'd all be dead. So there's probably some air there, but whatever. We got to ignore something. Okay, in this problem, what's the initial kinetic energy? Correct. What is the initial potential energy? Minus. What's the distance apart initially? That's right. The radius of the planet. Excellent. And that's because this one has negligible size, so we don't have to add any other radius. Okay. What's the final kinetic energy? Yeah. The equation would be, but the velocity is 0. What's the final gravitational energy? What's the equation for it? What's the equation for the final potential energy? Equation. Yep. And then what's the radius I use in the final state? What's that? Which is, now I know your math teachers might be groaning, but who cares? What is 1 over infinity, approximately? You know what I'm saying? We're pulling some loose math here. Whatever. We're getting the job done. Check this out. You agree that whole right side equals 0? And when I rearrange this, little m is going to drop out. The 2 comes over. V is equal to take a second and see if you get that. I'm going to read it again and make sure I didn't screw it up. I basically set this equal to that. The little mass drops. The 2 comes up. The square root drops it down. What do you think? I'll give you a second. Solving this for V. Let's plug in some numbers too. If you recall, mass of the Earth was what? 5.97 times 10 to the 24th kilograms. Radius of the Earth is what? 6370 kilometers, I think. Let's see if that's what it says in here. Yep, we're doing part B. Punching in the numbers. I got my calculator somewhere. Got it. Two times 6.67 EE negative 11 times 5.97 EE 24 divide by 6370 EE3, because the kilometer is an EE3, right? Kilometer 10 to the third. Now I'm going to square root that junk. Square root, answer, 11,000. I'm going to switch to kilometers. So just shifting it back by power of 3. So notice I did all the math in meters, and then I changed it back to kilometers at the end. Right? You can't keep the kilometers going in here because this is in terms of meters, right? So you got to switch everything out to meters and kilograms, do the math, then switch the prefix back. All right. Do a web search for AK-47s. The velocity, typical muzzle velocity, obviously it's going to depend on a number of factors, but let's just say one particular AK-47 could shoot bullets at 700 meters per second. Are those bullets going to escape Earth when you shoot them up in the air? No. So I kindly ask that when you finish this class and you're ready to party, don't go shooting your AK straight up in the air, because those bullets are going to come back down and kill somebody maybe. Got it? Just, yeah, if that's what you were planning on, do it. But yeah, it always, right, when you see people shooting guns up in the air to celebrate, it's always like, man, those bullets are going to come back down. Now, true, they're going to experience some air resistance, which is something we ignore. But right, they're still going to come. Yeah, it's just obviously as the planet rotates underneath, you're not going to shoot yourself probably, but you might shoot somebody else. Seems pretty unlikely, but let's just not do it. Okay. All right, another question. All right. So why is it advantageous to launch spaceships from Florida? Why didn't they do this in Maine? Right? Why are our space stations down in Florida and in the southern hemisphere? Not the southern hemisphere, the southern part of the states, like Texas, Florida. Why? What is the planet doing on a daily basis? Which points on the planet have the highest speed? Yeah, now look at the top, right? Look at this. Look at the North Pole, right? The North Pole is right on axis. It's not moving that quickly. It's rotating, but the actual distance it has to cover, points close to the axis, aren't moving that fast, right? V equals R omega. What about points near the equator? There's a large radius, and you're getting a lot of speed from the rotation of the Earth. In this problem, I need speed. Did I specify which direction it needs to go? It just needs to go away from the planet. If you're starting near the equator, you're going to have some speed from the rotation of the Earth. That's a little bit less fuel you need. And this gives you an advantage in launching spaceships. You have a little bit more kinetic energy to start with if you're near the equator. Cool? All right, I'm going to show you a simulation real quick. It's going to take me a second to fire this up. But this is one of the things you're supposed to do in your code, so maybe it'll help you kind of visualize what I'm hoping you will do. So meta. All right. So here's an example of this. Imagine we have these two objects sitting here. And when I run this one, if I launch it, it's going to go flying way out. Oops. This one going to come back. Oops, here, let me run it again, sorry. So now it'll auto zoom. It's going to fly out. And do you see it just getting farther and farther away? If I make a plot, you can see the center to center distance increasing, right? And see how the distance between them is still going up and up and up? It's escaping. So with this particular program, I did my math for me. And so let's say we go to 595. I'm going to run this program again. Watch what happens now. It goes really far up. You see it starting to come back now? See it? And it comes back and it collides. So it didn't escape. So the idea is if I look at the plot now, the center to center distance shows this thing got about, about 170 meters apart before it came back. So the idea here is I just came into here and I did some trial and error. And I found that at right about 597, so I'll use 596, this thing should go really far apart, but still come back. Right, so it's going. And so if I watch the plot down here, I can't tell if it's going to escape or not. And then right about now, I see it start to flatten out. So notice a small change in the initial speed. Now it's getting out to almost 350 meters, right? And it's going to take a long time, but now it's starting to come back. Can you see that in the plot? It looks like it's starting to bend back down. So I can tell it didn't escape. So the idea is it's very tricky to see if this thing escapes or not without the plot, because you can't really tell over a long enough time. You also look at the time I'm running this for. We're up to 3,000 seconds. So clearly, one of the things you want to do is you want to crank up your simulation speed when you're running these codes so that you could get this over with quickly, right? And so rather than have it run like this, you can come down to here and just crank up the sim speed. to maximum and see if it comes back. Oh my gosh, it's still taking a long time, right? Ugh. All right, whatever, you get the idea. It looks like I'm hitting the limits of the processor speed at this point. Here's a question for you. Take that back down. Let's say I do this direction. So now, instead of running this thing radially outwards, I'm going to shoot it straight up. What do you think is going to happen? I'll tell you what, let's go to 600. My claim was that if the momentum is 597 or larger for this set of numbers that I happen to use, it should escape. But now I'm not shooting it radially outwards. Do you think it will still escape if we shoot it tangent to the surface of the planet? What's your gut say? Okay, I have one response. I'll take it. Yes, it does. And this is what's interesting. Remember, the energy doesn't care about the direction you travel. It's still going. Now, clearly something is different. The shape of the path it takes is totally different. Agreed? But it does still escape. It just escapes in the opposite direction, which is not necessarily what we would expect. But if you look down here, it's still escaping, right? It's gone. This thing's out of there. Right? Well, what's going to happen if I run this thing at 590? Or let's just say, how about 555? Because you know me, I love 555. What do you think is going to happen? We don't have enough momentum to escape. So what should happen? What's that? Let's see. It's an orbit, right? So it didn't have, oh, so maybe the sim speed is too fast right now. Let's take it down a notch, right? So the idea is if you're going, let's slow down one more, power of 10. So obviously you know what to do if you get hung up, right? You can see this video again later and hopefully it will help you. Now in this case, if we don't have enough energy to escape, the kinetic energy is less than that negative potential energy. The total energy is negative here. So I guess what I'm going to say at this point is, to color code this, the 1/2 mv squared initial is less than the g m over r. Now notice I didn't put the minus sign here. That's because I moved it to the other side of the equation. So we're just talking about the size of the potential energy without the negative sign, right? And so if your kinetic energy size is less than the size of your potential energy, your orbit is trapped. You're negative total energy. If you have negative total energy, you can't escape. If you have zero total energy, you could just barely escape. Anytime 1/2 mv squared is greater than gmm over r, you do escape. Good on that?
Is it going to keep orbiting?
Yes.
It will fall down.
It is falling. It just never hits. You know what I'm saying?
Yes.
Which is weird to think that way, but it's constantly falling towards the planet. It just happens to be moving so fast it never hits the surface. Cool? Where is it moving fastest? Watch it.
Where it's closest.
Yeah. So here it's fast. And over here it's slow. Does that kind of make sense with your falling analogy? When you go up to max height, That's about right now in the orbit. You're kind of at max height, you're at your slowest. And then when you come to your minimum height or your minimum altitude, which is right about there, we see that you get going quickly. So when you're going up, you slow down when you're right. So it's falling all the time. Cool. Yeah. And if you want, you could look up terms like perigee and apogee. And I think I mentioned that somewhere in here, but yeah.
What does this graph for this look like?
What does the plot of the distance look like?
Is it like a sine wave?
Let's go look. Well, let me ask you this. Where does it spend more time? Does it spend more time up high? Or does it spend more time down low? Or does it spend the same amount of time up high and down low? What do you think, Peter?
More time up high.
Okay, so it's not going to be a perfect sine wave because the top should be wider. Let's go look at it. Does that kind of make sense with what you expect? You spend almost no time when the distance is small. Right, so let me clear all these annotations. Hold on. Right, so these points right here are the points when it's closest. And so it spends almost no time there, and then it quickly zooms around, and it spends a lot of time up here, far away. And so it's definitely sine wave-ish, like-ish, kind of-ish, but definitely not a sine wave. Agreed? So it's some sort of oscillation, but it's not a sine wave oscillation. Cool? All right, good question. All right, any others? Well, we got this up. Well, this begs the question, what's the easiest way to analyze elliptical orbits? Code them. Agreed? I'm going to come back to elliptical orbits in just a minute, but we're doing the same physics that you guys did last time in lab. It's just use force and kinematics, chop up the time step into really small pieces so that the acceleration is approximately constant. We're basically doing forces and kinematics, and we're discovering elliptical orbits. It's pretty amazing. All right, all right. Let me get out of here. Okay, and I want to go to this one. I always get a little confused coming out of the. Let me turn on some lights. All right. So if you get hung up on the lab, hopefully you can spot this point in the video, and maybe that'll help you out, right? Just freeze frame it and see what you need to see. Okay. See if there's anything else I want to say on this problem. Oh. Okay. Part E of 13.9. We never finished this. But maybe you're thinking about black holes. Look at this. If you set this to the speed of light, that gives you the mass to radius ratio for a black hole. This is a special type of black hole. It's not rotating. That's different if it's rotating, whatever, why, I don't want to go into that. But essentially, this tells you how much mass you need in what size sphere before an object can be a black hole. So if you want to have a black hole, right, light can't escape. Now, it turns out this is a numerical artifact that happens to match up to the Schwarzschild black hole, but in general, black holes are a lot trickier than this. But this does at least give a first inkling, though. There should be a mass that should be dense enough to prevent light from escaping. And you can even rewrite this in terms of density, too. So, all right, so I'm getting a little distracted there. All right. Sounds like my kids. I'm sure it's, I hope it's not. I think they're out of here. Hey, do you guys mind, let's try this. partying out there. All right. All right. Okay, 13.10. Where were we here? So this one. That did not work. All right. Okay, so let's say we have elliptical orbits. I just showed you probably the easiest way to do this was to code it. That is a terrible ellipse. That's slightly better. Not that great. But so maybe you've heard that the orbits around the sun are elliptical with the Earth at one of the foci. Okay, there's semi-major and semi-minor. I'm going to give you some advice here. Don't write any of this crap down. Okay, just listen. All right, let's say there's a planet here. Because we already told you the right way to do this is to code it, right? So I'm just trying to elucidate something here and talk about some general physics topics. That this is not something that's going to show up on the test in this way, but you can still learn something from listening. That's where I'm going with this. So do you agree? Let's assume this mass is really big. There'd be a force due to gravity right here. That's going to be Gm over r squared, where r is the distance between them along that dotted line. So far, so good? Well, my question is, what is the torque about this pivot point? Well, let's say I say this planet is the pivot point. How much torque is there due to gravity? Zero. Why? What's the reasoning? Good. Well, wait a minute. Do you guys know anything that's conserved if torque is zero? What is it? What's conserved if torque is zero? Okay, we just did a problem. Remember, if work is equal to zero, energy is conserved. If force is equal to zero, momentum is conserved. Yes. Okay, so that's saying angular momentum is conserved. So the way you could handle elliptical orbits is angular momentum. Now, to be fair, you could do angular momentum and energy, agreed? So we also know that work is zero here. Because we're assuming drag is zero in outer space, right? So you could say, you could do energy problems and angular momentum problems and have two equations and try and figure out something about the motion. Now, for reference, the angular momentum of a point particle, the original definition was R cross P, where P is the linear momentum here. And maybe I'll make that in blue. Sorry about that. Just learned, right? I like this problem because you have to think about those conservation laws. That's the part I thought would be good practice for you. Well, look at this thing. There's the velocity. And do you agree that velocity and momentum point in the same direction because P is mv? Right? Now, this is going to be obscure. I don't know if any of you recall this or not. There's a geometrical interpretation of the cross product. Does anybody remember what the geometry means for a cross product? I think I said it about 10 weeks ago, one time. Or maybe you know from math class. It's the area of the parallelogram created by these two vectors. So in this case, it would be this area right here. Well, I'm going to cheat and just draw a triangle here. This would be half of the area. So L, the magnitude of the angular momentum relates to the area. I know this is going to sound a little silly, but in grade school, you may have heard this. Satellites trace out equal areas in equal times. Have you heard that ever? Anybody tell you that? Okay. Whatever. This is one of those Kepler's laws that maybe you've read about on the internet or something. So you're going to hear something about equal areas. Well, that's just saying angular momentum is conserved. So the way this was originally phrased was they said, look, you can split this orbit into triangles of equal area. The shorter ones are going to be a little bit fatter. And then over here, they're going to get long and skinny, but each one of these areas should be of equal size. That's just a way to say angular momentum is conserved. So if you look this up on the internet, you may hear that. Everybody cool with that? All right, not on the test. I'm sure you're happy about that. But yeah, it's kind of interesting. So far, so good. All right. I would actually like to take our break right now. The logical spot to take the break is now. It's going to take me forever to erase the boards anyway. So I know it's a little bit early, but who knows? We may even get out of here early tonight. Okay. Or maybe we'll at least get some extra problems done. So let's take our break now. I can erase the boards and get ready for the next ones. I got 5:26. 538. Here we go. Yep. Oh, you mean about that? Yeah, what about it? Oh, so we used to do the big science shows, right? With all the kids stuff, right? And one year I challenged the chemistry department to a battle to see who could have the coolest demos. And we set up the stage like a fake boxing ring, and we had a referee, and then we had the crowd vote with decibels. And then, since this is on recording for all time, I have to clarify that I stood behind the chemists and made the crowd cheer loud so they wouldn't get swept. So yeah, so we kicked the crap out of the chemists in a demo off. But you know, to be fair, the best physics demos are basically chemistry demos too. So like chemistry has fireballs and explosions. So we did a bunch of cool stuff. That's all. And so we won 2 out of 3.
Me too, right?
What's that?
We've been like looking at that, wondering what it.
Yeah. And so then I know, here's the other part of it. I know the chemists sometimes teach it here. So I'm shaming them
Yeah.
the whole class period, knowing that they lost. So yeah, it's just, you know, just being a punk ass. I don't know. Yeah. So, yep, that's all that is. And then Angus and I signed it too, just so we could be like, yeah, we did this to you. All right, yeah, it's pretty fun, right? All right. I want to pick up with 13.14 at this moment. So Alan, do you remember this one? Do you have it in front of you, 13 point? Oh, okay, I'll draw it up, but I'm gonna pick on you in a second here. So I'm gonna try and color code this the same way as the solution. We've got a mass big M up here. And we got a mass big M down here. This picture you might want to draw slightly larger than usual, not outrageous larger, but there's a coordinate system. This is going to be our y-axis. It's going to be our x-axis. And there's a little point mass out here. That's going to be M3. And that's just going to be lowercase m. Okay. And so this one down here is going to be number 2. You got the problem now, Alan? So I just want to get Alan's opinion on this. My claim is this was like the bedrock of Physics 163 that we all started it from. Do you remember this problem?
I do, yeah.
Yeah, and one of the things in this problem is we have to deal with algebra and angles as opposed to numbers and angles. And would you say it's fair that we kind of use the math of this like intermittently all the way throughout Physics 163? Like when we did calculus on distributed mass or distributed currents, like Biot-Savart law, remember that?
Mm-hmm.
Would you say that's a pretty fair assessment? That we used it?
So.
Yeah, a couple of times throughout 163.
Yeah.
All right, so that's that was it. That's all you needed to say. I just wanted to point out that we're going to use this again and again and again. So this is one of those problems you want to put a star next to and just kind of be awesome at it, okay? All right. I believe we know that this distance here, the center to center distance here is 2a. And specifically, I think I said each one of these is also a in the problem statement. So each one of these masses is distance a off center. So we have 2 large masses. Those ones are going to be big M, and then 1 small mass, little m, and that's going to be number 3. Now, in this case, I'm interested in the net force on object 3. On 3. Well, there's going to be a force from object 1. Which way is that going to be? Show me with your finger. Which way is the force from object 1 on object 3? What the force on 3 due to mass 1? Does it pull or push? Pull. On 3 this way. Everybody okay with that? It should be pulled towards the center. Sorry if my picture's not quite angled right. Okay? Does that make sense? Similarly, there should be a force from 2 on 3, right? Which way is the force of 2 on 3? Yeah. Which one of these should be bigger? What's that? Yeah, they're the same size, right? They're the same size because do you agree the distances should be the same? And the masses are the same involved? So we should expect that these two have the same size. That said, what direction is the net force on 3? It's going to be on the x-axis, right? Do you agree this j hat part cancels that j hat part? So we know in our minds the answer should be something in the negative I hat. Agreed? By symmetry, we know the net force is negative I hat. So let's keep that in the back of our mind. But for now, let's try and do this problem mathematically. This is equal to G. Mass 1 is big M. Mass 3 is little m. And I want the force vector. So what do I need to do at this point? I want the force vector. I could divide by cubed as long as I multiply by. Is that correct? It's missing something. I've got the right m's. I've got the right. I'm missing something. Gravity is attractive. It's a negative force. Attractive forces are negative, right? R1 to 3 points this way. Is that the direction the force is pointing? Is the force pointing from 1 to 3? No, it's pointing negative 1 to 3. Agreed? All right. Now, help me. What is R1 to 3? Vector. In terms of the perimeter, oh, and in this one, I think I said a distance that I forgot to write down. X. We're told that this distance right here the problem tells us that that distance is x. Okay, so to go from 1 to 3, how far do I go in the I hat? If I go from here to there, how much do I have to travel in the I hat? X, positive or negative? From 1 to 3 is what? Positive x in the I hat. I'm going from 1 this way. How about the j hat term? What's that going to be? Negative a. You go x in the I hat, negative a j hat. Now, obviously, the force points the other way. That's why we have that minus sign right there. This is crucial that you get this. I want to make sure you get this, because if we understand this, you could do the coding, you could do the labs next semester, you could do the homework problems next semester. If you can't do this, you're just toast. So it's okay to be confused as long as you just tell me what's up or take a second if you need it. And maybe put a star next to this problem and redo it again without looking at the video, right? Just this is one we're doing twice. Okay. Now, what's R13? The distance, what's that going to be? If I just want the distance, how would I get the distance between them? X squared plus A squared. And then what do I have to do with that? You're right. And then it turns out from experience, I don't want to write the square root. I want to get in this habit. If I raise it to the 1/2, do you agree that's the same as the square root? And just from experience, it just ends up being convenient. That's all. You are right. Everything you said was correct there. Okay. Well, at this point, I'm ready to plug in the pieces and we got the force. Agreed? It's going to be G M M over, aha. If I cube this, what happens to the exponent? Instead of being 1/2, it will be 3/2. When you cube something, right, the exponents, right, I take 1/2 plus 1/2 plus 1/2, that's 3/2. Okay. And now here, I'm going to put that minus sign out front. I'm going to put this minus sign out front. I need a little space here. I want the minus sign sitting out here. And then I get and notice there's the force. We're done. Before going on, let's make sure it's pointing the right way. It's actually in the negative I hat and positive J hat. Do you agree? It's left and up. So this minus sign is pretty freaking crucial. Everybody good? Pointing the right way. Now you might say, I don't like this, Jorstad. I like doing SOHCAHTOA. Okay, I'll show you that way really quick, just in case you like that method. But I do believe that this way you end up getting used to it and liking it more, because this way also works in 3D. In the next class, we have to do 3D. On your exam for this class, on the final, it's going to be a 2D problem. So let me show you this another way. I could get the magnitude of the force, and I could put in some angle here, theta, and it would be negative cosine theta in the I hat plus sine theta in the J hat. That would also work. Do you guys buy that? The magnitude, and then you say cosine theta in the negative I hat. So take a second to kind of feel this through. This is, I think, also very useful to understand. You good on that? But now, how do I get cosine theta? Well, I'm going to draw the triangle again. This side of the triangle is A. This side of the triangle is X. What's this side of the triangle? No, just in terms of X and A, just like in terms of distances. You're right that yeah, or maybe I misheard you. Yeah, it's the X squared plus A squared to the 1/2. Do you agree? Like Pythagorean theorem. Is that good? And so if this is theta, what's cosine of theta equal to? Adjacent over hypotenuse. What's sine of theta? Did that make any sense at all? Do you agree it's basically the same? And you might be saying, wait, this x is negative. But remember, we got a negative x I hat. Here we have a negative x I hat. I have a positive a j hat. I have a positive a j hat. Same problem. Doing this method is the same as doing SOHCAHTOA, but you spend less time on it after you get used to it. So it's a faster way to do SOHCAHTOA. That's it. Cool? We didn't talk about this in week 1 because I didn't want everybody to quit. But now that you can see it, you can probably appreciate it slightly and be like, okay. Now, wait a minute. This has x squared plus a squared to the 3 halves. I only see a 1/2 here. Where are the other halves? There's 2 more halves. So it's there. It's the same problem. Everybody good with that? Now, in order to make room to do the rest of the problem, I need to erase all this. You want a shot or not? Photo? Or are you good? Just because I know sometimes, yeah, you like to. But I actually appreciate that you were listening rather than writing so that you could pay attention. But I'm just letting him get a photo of that if he wants it, because sometimes he likes that. Any questions about that while we've got it? Did you get it? Okay, all right. Better safe than sorry, right? Okay. All right. So now, let's get F23. It's going to be G M little mass all over negative we'll come back to that. Right? It's the same procedure every time now. I write down this equation. I figure out R23. What's R23 in this case? Is it going to be the same as R13? No, what's different? What do you think it's going to be? Look up here, follow the pattern. How much in the I hat, how much in the J hat? We're going from 2 to 3. Yes, both values are because it's positive X, positive J hat now. So it's only one of them gets flipped, which is why only the J hat drops out. Good job. Obviously, we don't need this plus sign in front. I was just doing that for emphasis, okay? So what's R23? The magnitude. Is the magnitude different or is it the same as the previous one? Same distance. So now when I plug this in, I'm gonna bring the minus sign out, just like I did on the last one. Remember, we brought that minus sign out? X squared plus a squared to the what? 3/2. And then we're timesing by that r vector over there. If I get the net force on 3, checking what color I used. Whatever. Vector. That should equal these two added up. Is this making some sense? And when I add them up, take a second to look. I drew them this way so that you would see everything out front is exactly the same. Do you see that? That's why I was moving stuff around. And now what's going to happen to the j hat component when we add these two together? It drops out. This one's negative j hat, that one's positive j hat. Kind of got smudged there. What's going to happen when you add the I hats together? What do you get? 2x. Do you see that? So when you add this together, it's basically going to be this with a 2x I hat. Or I'm just going to write it that way. Negative 2g m m x I hat over some crap. It looks ugly, but it's easy if you practice. If you don't practice, this will just kill you. What do you think? There's the net force. All right. I did the same thing that I did in the earlier lecture. Isn't this part B, not part A in the question? I was so excited to do the force here, I forgot to do the potential energy, so I apologize. But I happen to know you could do the potential energy really quick. Should we go back and do part A really quick just to make sure you feel good about it? But so this was the answer to part B, not part A. I apologize. Everybody good on that? All right. Totally spaced on it twice. I don't know why. I'm excited about the force. So let's go back and do part A. I'm just going to draw a picture here really quick, a small version of it. We got a blue one. We got a red one. Then we've got a black one here. And we labeled these 3, 2, and 1. When you're doing potential energy, this part is in 163 too. Okay, it's also in 163. I want you to think this way. The energy comes from each pair of masses. How many pairs are there? How many different possible pairs can you make from 3 things? Here's a trick. Start by writing them out this way. First, start with number 1 and give me one object the next lowest number, 2. That's one pair. Agreed? Are there any other pairs we can make with object 1? 1 and 3. Is that all possible pairs we could make with object 1? Yes. So move on to the next lowest number. 2. What is one object we could pair with 2? Number 1. However, have we already counted that? Yeah. So go to the next number. 3. Got it. There's no more. Now go to 3. 3 could be paired with 1. Already got it. 3 could be paired with 2. Already got it. Oh, we're done. And so if you write them down in this order, you don't have to think too much. And less thinking means more getting on with your life. Okay, I love physics. I love it. But you're not going to sit there on your deathbed saying, gee, I wish I'd spent more time figuring out the order of pairs in a gravitational potential energy problem. So you want to get this done. So just do it quickly. This is my recommendation. Got it? All right. Well, let's do this. In this case, what's the gravitational potential energy between objects 1 and 2? What's the formula for it? Negative. Yes, you remembered it. Negative, and then it was a big G. Then what? Which M? Was it little m or big M? Do you remember? Yeah, so this one was a capital M. This one was a lowercase. No, this was also a capital M. This was the lowercase one. Is that right? So with the first one, 1 and 2, we're going to get 2 big M's. And then what? Divide by what? 2a, the distance. Is it squared or not squared? Not squared, correct. The force has powers in it, but the energy is just to the 1. Yeah. All right. Next. The next term is going to be negative G mass 1 mass 3. This is little m. What's the distance between them? Do you remember from the previous problem or from part B? What was the distance between them? Excellent. And then do you agree the third term is actually going to look the same? Except it's a red M, but it's still big enough. Piece of cake, agreed? So do you agree energy problems are a little bit easier to write down than all that vector crap? This is why at the start of class today, I was saying, when should you use energy? Anytime you can, you want to use energy, except sometimes if I ask for force, you've got to do force. Or if I ask for acceleration, you have to do force. All right, so that's part A. Everybody good with that? Next, in the interest of space and just knowing how much board I need, I'm going to do the following. Erase that picture. I'm going to put a box under this. All right. Part C says what value of X gives the most force? And for Zoomers, let's go back to that other board just so you can see it. I want you to think about something here. I claim that there's going to be some spot that gives you more force than any other spot on the x-axis. Now, let's start here. What's the easiest value of x to work with? 0. If you put the mass right here, how much force is acting on it? Net. What's the net force if you put the little mass right here? 0, because it's up and down. It's all j hat, the j hats cancel. Let's go the other extreme. What if I go really far away? What's going to happen to the force if you go way over here? In general, as you go farther away, what happens to the force? Stronger or weaker? Weaker. So do you agree it's 0 at the center, and then way over here, it's going to go to 0 if you get far enough away? To me, it makes sense that there's got to be somewhere in between where the force is biggest. Do you agree with that? Okay. Does this equation reflect that information? Look at it. What's the force when x equals 0? 0. If x gets really big, do you agree a doesn't matter and I get x squared to the 3 halves? I get x cubed in the basement. So I have x over x cubed. As x gets really big, do you agree this goes to 0? This makes sense. All right. So now I'm just going to write this over here so I don't have to keep changing boards. I know that the force I think it was. I want you to tell me 2 ways to find the maximum. What are some ways we could find the maximum force magnitude? Give me any method for finding the maximum in the universe with infinite budget, other than paying someone else to do it. That's a good method. Okay, that's a good method. You could make a code and literally try different spots and look around for it. That's not the method I wanted to go with, but that is actually a good method. It may be time consuming if you don't guess right. Not bad. Trial and error is a valid method, sometimes slow. What's another method? He says he's done. I want the most force. Maybe if I change that word most to, I want the max force. Solve for x? What do you mean? You're on the right track. We got to do something before we set it equal to 0. What did you do in calculus class when you wanted a maximum? Take the derivative and set it equal to 0. So what I heard was I could take the derivative with respect to what? No. X. I want to take the derivative with respect to this variable of and set that equal to 0. Solve for x. And sometimes we call that x critical. Do you remember that in calculus class? That works great. What's another method? Plot it. If you plot it, can't you just see where it's biggest and say that's the number it's biggest? Now, why am I doing this to you? I'm not trying to torture you. It's just like in the real world, sometimes it matters where the biggest value is, right? And now, if you didn't have an instructor here to help you, and let's say part of your job is somebody says, look, I need to find out the biggest load that this cable can take before it's going to snap. Well, one thing you would do is get a mathematical expression, do the calculus, plug that calculus into the internet, and make it do the calculus for you. But then you might also check that with the plot to make sure they're consistent. Anybody can screw this up. You got to check as many ways as you can before you hand the work off to your boss so you don't get fired. Right? Because if you do this wrong and something crashes, that's your job. You're out. So, all right, the point was, this in general, right? I know in math class, they just tell you to do this step. Yeah, but we need to be employable. So we need to verify that with a plot. That's my extra spice that I would add in there. Is everybody cool with that? Shove it into Desmos is what many students might say. I don't use Desmos. I would use Wolfram Alpha, but it's the same thing. Okay. All right. Now, at first, this derivative looks ugly, time consuming. Well, it is. It is time consuming. But if you learn a few of the tricks that I'm about to show you and remember these, when it comes up again and again and again, at least for physics classes, this comes up all the time. Let's just figure this out and do it. Step one, factor out the constants. Negative. What are all the constants in here that I can factor out? 2, g, the minus sign. What about the masses? Are they constant? How about x? Is that a constant? No, that's over a derivative. How about I hat? Is that a constant? Yes, I hat is always to the right. That's constant. Now I got my derivative here. And it's a little bit less scary looking. I'm going to set that equal to 0. What's going to happen to all the constants? Yeah, we could divide through, and all that's going to disappear. Now, how many of you remember the product rule versus the quotient rule? Now, for me, I don't like the quotient rule because I have to think more. So why do a quotient rule if you don't have to? I'm going to set this to 0 and raise this up. Just trust me on this. All I'm doing is I'm setting this up to do the product rule. So that's one less minus sign I have to memorize from some stupid class that I don't take in 5 years, right? So it's now I've just moved this exponent upstairs, made it negative. Now it's easier for me. F prime G plus G prime F, and the minus signs will work themselves out. All right. Well, let's start working our way through this. Take the derivative of the first. What's the derivative of the first? 1. Derivative of the first times the second. I'm done. Next, I add to it the first times derivative of the second. Walk me through it. How do I take the derivative of the second term? Okay, so what's the first part? Bring the power down. What's the next part? I break the power down. I have to remember this shit to the power minus 1, right? Negative 5 has. Or are we done? Or is there more? Take the derivative of what's inside. What's the derivative of what's inside? Yeah, do you agree that a squared is a constant, so that's going to drop out. All of this ends up being 2x. This derivative happens all the time in physics. Well, not all the time, about once every 4 chapters, but still, it's enough that you should know it, okay? Derivatives with fractional powers. Okay? Typically, we see this all the time. Oh, and then then we're done. So we set this equal to 0, right? We didn't finish the equation. That was just an expression. Now it's an equation. Usually we see this 2 cancels that 2. We get our minus sign. You could rewrite this at this point back into normal. So now undo the negative powers, and what do we get? 3x. And there's another x there, so it's 3x squared, isn't it? Do you agree? 3x squared negative. 3x squared negative. So far, so good. At this point, do you agree the rest of this is pretty easy? Just move it around, solve for something. If you want, I found out that it's what? A over root 2. And I worked this out in the solution. I did step by step, so you can see it in the solution. You can't find that. This value of x gives the most force. How could we verify that this is a maximum if we didn't have our, we know it's going to be a maximum in this case because we kind of thought it through. It's 0 here, it's 0 there, it's got to be big in the middle. What's the technique in a calculus class for checking if something's a min or a max? Sorry, I'm torturing you all here. Second derivative test. Do you remember that? You take another derivative. If the second derivative is positive, it's concave up, it's a minimum. If the second derivative is negative, it's concave down, whatever. So here, it's going to be, I think it's actually going to be negative because the whole thing was negative. So it's actually a minimum force, but it's going to be a maximum magnitude, however you want to think it through, whatever. Point B, you could take this value of x, plug it in there, and we should get a negative I hat force, but that will be the largest negative I hat force. If you wanted to check it, you could do a second derivative test. If I don't write it, students don't hear it. I'm going to write it. That would be unpleasant, though. You agree? If this is the first derivative, taking the second is going to be pretty ugly. So that's why it was nice to just think it through. What's the other way you could verify it's a maximum or a minimum? Plot it, right? That's the advantage of the plot. You just see it. All right. Is that enough on this? We do this again in 163, at least 2 more times. Once for magnetism and once for electricity. So you're going to see this again. All right. So far, so good. Let's talk shortcuts, right? This was the right way to do it. We talked about all this. I want to go back and say one more thing here about this. I want to point something out here. Let's say I want to get the net force on 3. We talked about this. We drew a picture and we said, look, I know that this one's up and this one's down. And so I could actually do a parallelogram rule here. Oops. Right? Tail to tip, tail to tip. Or I could do it the other way, tail to tip, tail to tip. From experience, I know the net force points this way, agree? Isn't that the same thing as saying F net on 3 is equal to 2 times F13 vector in the x direction only? So if I keep the vector on here that says take the x component with the I hat, and that would give me the correct answer. Do you agree with that? By symmetry, I could just get this one's x component and double it. Isn't that a lot faster? Because it's literally half the work if you see this. I do this problem really well, and I'm like, dude, just grab the I hat part and double it instead of doing all this crap twice. Agreed? So that's the shortcut that if you start seeing these kinds of things, you can use symmetry to reduce the amount of labor in a calculation. I don't know, I just thought I'd throw that out there. I think we beat the crap out of this problem at this point. Good on this? Okay, if you're looking for one problem to do, oh, Alan, go ahead.
Okay, I could add anything. I think symmetry is very important. I mean, you don't need it to do the calculations, but it saves you so much time in your homework and your exam. Like in 163, you could use this like on 2 chapters, right? Like,
We did, yeah, we hit this, yeah. Oh, because there's forces, fields, magnetic fields, magnetic forces.
Yeah, and I just remember the symmetry for these problems, or kind of like looking out for symmetry, and it just saved me so much time in the exams, up to the point where like I walked out of exam 1 like 30 minutes early or something with a good grade.
Yeah,
So
yeah,
looking out for symmetry is just very nice to know.
yep. And would you say, I think this is true, I generally speaking don't spend time on symmetry in this class, but we do it all the time in the next one,
Yeah.
right? Yeah, yeah. So, and I will hammer this, the symmetry argument, exactly what Alan, I totally agree. If you see it, the problems become much quicker, and you know time is at a premium when you're on one of these tests, right? So, yeah, thanks, Alan. Anything else you want to say?
No, that was it.
Yeah, yeah, symmetry is useful, hugely. And we'll practice it next semester. Yep. All right. I want to do a couple more problems here. I'm going to point out, look at 13.20. Look at 13.20. Does that one look nasty or what? 4-point masses with a 5th one way off to the right. Don't worry, we got 20 minutes. I'll pick up the pace. I can tell you guys are falling asleep here. I wanted to do that one slow. Now I'll pick it up, okay? All right. I'm not going to spend all day on this. I'm not going to do the problem. I'm going to sketch it out. So let's say I think we're going to say this is the X, this is the Y, and this is the Z in this problem. Yep. And so we've got some masses here that lie on a square. Whoops. In the XZ plane. So that's supposed to be a square. It's supposed to be centered. It doesn't look very centered. Okay, so to be clear, this red square is supposed to lie in the XZ plane. It's hard to draw. Somewhere sitting over here, there's another mass. I'm going to call this one 5. And it's some distance over here, Y. This is mass 1, 2, 3, 4, I believe. Yes. Look at this picture. What direction is the net force on 5? The net gravitational force on 5. -1. It's in the -y by symmetry. Isn't this almost exactly the same as the last problem? So what's the move that we're going to do if you had to do this problem? Get R1 to 4 vector. Now to help you out, R1 to 4 is going to be this way, and that's side over 2. It's going to come this way, S over 2, and it's going to go that way, Y. So I think it's -S over 2 in the I hat, right? That's negative I hat. It's negative S over 2 in the K hat, because this is the Z axis. And then it's how much in the J hat. Why? Does that make sense? Where would you go from there? Once you know this, couldn't you get R14? And that's just going to be some big ugly thing to the 1/2. Notice it's not going to be S squared. It'll actually be S squared over 2, because you get S squared over 4 plus S squared over 4. So again, you get an S squared over 4 plus S squared over 4. 2 of those together makes a half. Oh, wait a minute. We don't want 1,4. I meant 1,5, didn't I? We're going from 1 to 5, not from 1 to 4. Do you agree? Look, I made a mistake there. Everybody, do you agree?
Yes.
We're supposed to be going from 1 to 5. I apologize. Let's fix that up. So we're getting the force of 1 on 5. Sorry about that. That's just garbage you plug in. That's nothing, right? It's ugly. Sometimes the answers in the real world are not pretty. They're ugly. So you just shove in a big ugly thing. If I want the net force on 5, what would I do then? I'll give you a second to catch up. And remember, I already told you, I'm not doing a 3D problem like this on the test. This is just to help us learn and feel, okay? So, right, this is a great problem. Like if you had to pick one 3D problem to do to get extra practice, this is it, right? So it's okay to do this problem for practice. It will make you stronger on test day. It's sort of like lifting more than you need to so you get strong. That said, how do I get F net on 5? You told me, what direction is it? Yeah, so what would I do? 4 times the J hat part of this garbage, right? Because there's 4 masses. This one's K hat, or this one's I hat and K hat will balance this one's I hat and K hat. This one's I hat and K hat will balance that one's I hat and K hat. And so when you work it all out, you just get the J hat part and quadruple it. All right, what do you think? Not too bad, right? And that's what Alan was saying. We use these kinds of problems all the time in 3D, because in 3D, we have to do vector cross products all the time. It has to be 3D. So far, so good? There's not enough time to do every problem, so I want you to put a big fat star next to 13.21. That's a great problem for you to study. You've got potential energy, you've got gravitational force, you've got directions. It looks a lot like I like to write test questions where everything's got distances algebraically. So you should do 1321 at home. Got it? I got the solution written up in both styles so you can see both styles if you're a SOHCAHTOA person or if you're an R-hat person. All right, what else? I need to talk about 2 special topics here for physicists. So at this point, I'm going to do these 2 topics. If you guys just want to sit there and absorb, That's fine by me. So the two topics that I'm about to do, I want you to just relax, watch them, observe. If you're a physicist, you should know them. If you're not, who cares? If you're a chemist, they might relate to some of what you do in chemistry as well. So that said, I need to erase the board. You guys can pack up your notes. I'll be done erasing in a second. I'm going to do two quick topics and we're out of here. And that's chapter 13. So definitely chemists and physicists are going to use this stuff. Give me a sec. I'm still erasing. Good? Everybody? Good. So what we're about to talk about, there's still some good learning and review in there. But it's, yeah, so it's good to hear this stuff and kind of think about it. But when you practice for the exams, you're probably going to do different types of questions to practice for the exams, including for the parts that are covered here. So just trust me, listen to me, pay attention, learn something, and that's it. Okay. Just finishing erasing the other board, Zoomers. Ooh. All right. Okay. So I'm looking at page 124. You don't need anything. But for the records, this is a topic called reduced mass. It shows up in chemistry. Up until now, we've always said the central object was really heavy. Like one of the objects was so big it didn't move. The obvious question is, what if it does move, right? So let's say we have a mass here. Let's say we have another mass here. Let's say this one isn't infinitely large. Maybe it's only 10 times bigger. There's going to be some center of mass. Agreed? In this case, this object, well, both objects are going to have the same force on them, right? In terms of its magnitude. What I've done, just do it a little reduced mass. So in this case, there's always going to be a force towards the center, and this one's going to go on a circular orbit. I got to stand in front of this, like this, right? And as they move, they're always going to be diametrically opposed. So this one's going to go on a different circle. Not here. And to be clear, this one has a radius to its center. This one has a radius to its center. Okay? If I did the free body diagram, and let's just say this one is 1 and this one is 2. So let's say this is mass 2. Let's say this is mass 1. I could say F1 on 2 is equal to, now most of you would probably say, oh, there's some speed here. Let's say this one's going down, some speed V2. This one might have some speed V1. We could say mv squared over r, but I want to do this in rotation land. So I'm going to say it's mass times r omega squared. Right? Remember that this is a different way to write AC. Now, when we look at it, the radius of circular motion is not the center to center distance. Do you agree? The circular motion is related to this radius right here. If you use the center of mass equation, we could learn that the red object's radius is the entire radius times this special factor if we do center mass. And if you've done center mass problems, you'd be like, yeah, that seems plausible. Okay. Well, when I plug all this crap in here, notice I get little m times this factor. Now I want to point out, look at this entire term right here. This is sometimes given a new name, mu, as if we weren't using mu enough already. Let's throw another mu in there. And notice, what are the units of mu in this context? What are the units of this thing? Nope. Kilograms, because this is kilograms squared on top, but kilograms on basement. Agreed? Let me ask you this. Is this bigger or smaller than little m? When you put all this crap together, look at this version of it. Look at this number. Look at the red number right here. Is that bigger or smaller than 1? Smaller, right? M over m plus some crap is less than m, or is less than 1. So this is a reduced mass. If you ever do, have you heard about reduced mass in chemistry before? The spectroscopy of the hydrogen atom. At some point you may hear this. It turns out when you have two bodies that are orbiting, you can actually redo the problem as if this mass has the full radius, except you reduce the size of the mass. This is a mathematical trick, not on the test. Everybody happy with that? You want to learn more about that? Great. Last one. I'm going to go quick. Okay. This one, for reference, is, I can't help it. I'm a very excited individual about this one topic. If you're a physics major, you should know both of these, right? But this is on page 121. And this is 13.12 for reference. I'm going to go super fast here. And you're going to see this again in 163, so it's not bad to see it. Let's say you have a big planet. Let's say this thing is mass capital M, radius capital R. Let's say there's a point mass here. Let's say this is little m. Let's say it has negligible size, but let's say the altitude here is h. Most of you know the potential energy would be negative G, mass over R plus H. For no good reason, I'm going to factor out an R. To do that, I have to rewrite this in a weird way. Take a second. Do you agree that that's mathematically legal? Okay. Now, at the end of this, I think you'll be like, oh, okay, that was slightly interesting. Just trust me. Now what I'm going to do is I'm going to rewrite this again. Negative G M M over R times 1 plus H over R to the negative 1 for no seemingly good reason. I'm going to now write it this way. If H is much, much less than R, H over R is much, much less than 1. Do you believe that? If h is small compared to there, just divide both sides by r and you get that. I'm going to let delta equal h over r. And now I'm going to rewrite this up here. Negative g m over r times 1 plus delta to the negative 1. Now this seems silly, but this is a standard physics procedure. Okay? There's a thing in every physics textbook called the binomial expansion. Okay? The binomial expansion looks like this. If you have a binomial like 1 plus or minus a small number raised to some power, doesn't even have to be an integer here. This is approximately equal to 1 plus or minus n delta plus n times, what is it? N minus 1 over 2 factorial times delta squared plus higher order terms, etc. Okay? This is basically Taylor's series. Okay? Now, I just want you to hang with me for a minute. Okay? This is what physicists do for fun. If delta is a small number, do you agree delta squared is going to be much smaller than delta? And delta cubed would be much smaller and much smaller? This is the whole point. We could take this expression, which looks really hard, and if delta is small, it's approximately equal to this. You take something that's got a god-awful exponent on it, and you reduce it to something linear. Linear functions are easier to work with. Check this out. U equals negative g m m. Hang with me. Hang with me. This would be 1 plus negative 1 times delta. All right? Now I'm going to plug back in all this garbage. I'm going to flip the signs. We get U equals G M M over R times delta minus a constant. All right? This other term is this. Oh, we can just write the constant. But this is a constant. Am I still on?
Yeah.
Okay. Wait. What is this? This is the good part. It's going to be M. Just bringing that forth. I've got a G M over R squared times H. You agree? Delta was H over R. You buy that. Wait a minute. What you're telling me is this is M. What is that? The first problem we did in this chapter? MGH. This is showing you that, remember that old MGH formula we used? Because only changes in potential energy are physically meaningful, the minus constant, we could just set a different reference level. We're done. This is a 2 hours ago. That's it. Get out of here. Ah.